Hello, I'm Jason Hartline, and I'm a professor of computer science at Northwestern University. And I'm going to be lecturing today on Bayesian approximation. We're going to be looking at a number of the foundational results in this area. And as further reference, you can refer to chapters 4 and 5 in my textbook manuscript, Mechanism Design and Approximation. I'm going to start out with a motivating example connecting uh, a area called prior independent approximation with some standard auction theory results. And so to start out with the definition, so prior independent approximation is looking at identifying mechanisms that work well regardless of the context they're in. And so we'll say a mechanism APX is a prior independent approximation if for all IID distributions F, the expected performance of the mechanism APX is at least a 1 over beta fraction of the expected performance of some benchmark mechanism. In particular, probably the revenue optimal mechanism for the distribution F. Okay. So I'm going to go over some quick notation. So we're going to be looking at APX of n will be the revenue of the efficient mechanism on n agents. So we'll be considering a single item auction scenario. We'll be considering n agents, and we'll look at, for example, the second price auction, which is the efficient mechanism in this context. And we'll let ref of f of n be the revenue of the optimal mechanism on n agents. And one of the things you'll notice about our notation is that we denote with the f the fact that the reference mechanism does indeed depend on the prior distribution, whereas the approximation mechanism does not depend on the prior distribution. Great. Now, one of the central results of auction theory is the Bulow-Klemperer theorem, which says that if the distribution F is regular, then the efficient mechanism with n plus 1 bidders has at least the revenue of the optimal mechanism with n bidders. Okay, and so what we're going to be doing right now is showing that in fact there is a prior independent approximation result lurking here in this theorem. Corollary is that, again, if I have regularly distributed values, then the efficient mechanism is a n minus 1 over n approximation of the optimal mechanism. So in other words, if I have 100 agents, then I get 99% of the revenue of the optimal mechanism running the efficient auction. Okay, so let's look at this proof. Okay, so we'll start out with the statement of the Bulow-Klemperer theorem applied to n minus 1 agent settings. So the Bulow-Klemperer theorem here says that the efficient mechanism with n agents has at least the revenue of the optimal mechanism with n minus 1 agents. Okay, And in a second, we'll prove the following claim, that the optimal mechanism with n minus 1 agents is an n minus 1 over n approximation to the optimal mechanism with n agents. Stringing together these results, we'll see exactly the claimed desired theorem, which is that the efficient mechanism with n agents is an n minus 1 over n approximation to the optimal mechanism with n agents. Okay, great. So we're going to be looking at a particular n minus 1 agent auction. We're going to draw one dummy agent from the distribution. We are going to simulate the optimal mechanism with n agents on the n minus 1 real agents and this one dummy agent. If the dummy agent wins, I'm just going to reject everyone. Otherwise, one of the real agents wins, and we'll output that simulated winner. Great. Okay, notice that the chance the dummy wins is exactly 1 over n because the dummy agent is one of n agents in total. Thus, we can conclude that the revenue of this auction is a 1 minus 1 over n fraction of the revenue of the optimal auction with n agents. Why is this? Well, we have n agents, a 1 minus 1 over n fraction of the time. The outcome is the same as the outcome as the optimal auction, and 1 over n fraction of the time, we ended up getting the dummy agent as the winner and having 0 revenue. So the revenue is a 1 minus 1 over n fraction of the optimal revenue. Okay, well, this was an n minus 1 agent auction. Of course, the optimal auction for n minus 1 agents is larger, has larger revenue. Thus, we've concluded our theorem that the optimal mechanism of n minus 1 agents is an n minus 1 over n approximation to the optimal mechanism's revenue on n agents. Okay, and that concludes our proof that, in fact, the Bulow-Klemperer theorem, which is ordinarily stated as a theorem about the increased revenue that comes from competition, actually shows us that competition, is sufficient for driving revenue, and in fact means that employing techniques from optimal auction design like reserve pricing is maybe not as important as we might have thought. Okay, so I'm now going to talk a little bit about the philosophy of approximation. So again, we'll say a mechanism APX is a beta approximation of some target of ref if APX is at least a 1 over beta fraction of ref. Now, I've stated this sort of abstractly, and there might be assumptions of the scenarios we are considering here that are implicit and not listed in this definition. So why is this definition interesting? So I'm going to talk a little bit about the philosophy of approximation. Okay, so a first thing about approximation is that simple mechanisms are often practical, and when the optimal mechanism is complicated, this complexity may make it impractical. And so we may like approximation mechanisms just because they're simpler than the optimal mechanisms. Moreover, uh, there's what I call the method of approximation. So the method of approximation attempts to use the use approximation analyses to understand fundamental properties. Okay, and so in particular, um, what I'm often interested in understanding is if I have a model uh, that has some features and I'm studying optimal auctions, I want to understand which of the features of this model are important modeling features and which are unimportant details. And I'd like to understand this because uh, if I have important modeling concerns, I better make sure I model them when I consider this kind of economic question. On the other hand, if I have unimportant details, uh, I would prefer not to model them and hope that the results that I gain and understand without modeling them would translate and be robust to those details. And approximation can help you identify what are details and what are not details, because you can ask whether, for example, mechanisms designed without some feature or without taking into account some modeling assumption are good approximations of mechanisms that are designed with those features or with that modeling assumption. And if these mechanisms are a good approximation, then those details maybe aren't, those features maybe are details and they're not that important. On the other hand, if there does not exist a good approximation without modeling or treating those details, then these are important details that I better model. And so we're going to look at a few examples here. We just saw that prior knowledge of the distribution may be a detail. Why is that? Well, the optimal auction indeed it depends on the distribution, but we just saw that we get an n-1 over n approximation to the optimal auction without needing to know the distribution. So in some sense, that knowledge we might be able to consider a detail. On the other hand, I could ask you about whether transfers are a detail. And suppose I wanted to design an efficient auction. And I said, well, can I design an efficient auction without transfers? And the answer is no. You can't design auctions that are very efficient without transfers, whereas with transfers, you can design the efficient auction. And so transfers are not a detail. They're an important feature of a model. If you have transfers, you need to use them. And if you don't have transfers, maybe you should be worried and try to figure out how you can get transfers in your model. Another thing which is going to come up later in the series of lectures is collusion. Is collusion a detail, or is collusion an important feature that we better make sure to model? And what we're going to conclude later is that actually collusion is a detail. It's not that important. And the reason why we'll be able to conclude that is because we'll be able to come up with auctions that are robust to collusion, that have nearly the same revenue as the optimal auction that ignores collusion. Great. And so, so my final point is that approximation mechanisms, in fact, are often very robust to details. I have this nice illustration, which is due to Pablo Picasso. It's a study of a bull that he did over a 1 month period in the 1940s. And you see here, he starts out drawing in the upper left corner with very detailed drawings of a bull. And he finishes in the bottom right corner with distilling the essence of what it means to be a bull. And this is, I think uh, what we're trying to do uh, with science and economics, and in particular mechanism design. We're trying to really understand, what makes mechanisms good in various environments, and what are properties of those environments that are really important that we have to consider to be able to understand what mechanisms are good. And so we're trying to distill it down to the essential characteristics, and yeah, like Pablo Picasso did. Uh, Great. So the last segment of this section of the lecture is a very brief review of auction theory, where I'm gonna talk about the value model, and I'm going to review quantile space and revenue curves, which are sort of fundamental constructs for thinking about revenue optimal auctions. Great. So we're going to have an independent private value model where agent I will have a value drawn from a distribution Fi, and we're going to be studying optimal auctions. And as you are familiar with from previous lectures, optimal auctions can be understood very well through this concept of virtual values, which I've defined here. The virtual value for an agent with value v is their value minus a term, which is 1 minus the CDF of the distribution, capital F, divided by the density function of the distribution. Great. So we're going to be looking at auctions in quantile space, where rather than thinking about the agent's values, we're going to be thinking about the agent's quantile, or their strength relative to the distribution of values. Okay, so low quantile is going to be a strong agent, and a high quantile is going to be a weak agent. Okay, and there's going to be a mapping, uh, which I'll call the value function. It's also called the inverse demand curve, which maps between the value space representation, where I have a distribution, and the quantile representation, where I need to map quantiles into values. And just to illustrate this scenario, so typically I have a distribution function. Fi of vi. And what does this mapping into quantile space do? It takes this plot and it rotates it counterclockwise. Okay, so this is the rotation we might get rotating this plot counterclockwise. Great. I will denote allocation rules by y. I'm going to write them in quantile space. So y tells me the probability, yi tells me the probability that agent I is going to receive the item as a function of the agent I's quantile. So allocation rules are written in quantile space, and strong agents have low quantiles. So allocation rules are decreasing functions. Uh, Great. And I'm going to write payment rules, which also in quantile space as pi of qi. Great. Revenue curves plot the revenue I can obtain from an agent as a function of the probability that I sell to them. And I'll denote that probability that I sell to them as QI. Okay, and revenue curves are very easy to express in quantile space. So the revenue from selling to an agent with probability QI, one way to sell to that agent is to post a price equal to VI of QI. This is the value of the agent with quantile QI, and a QI measure of agents from this distribution are going to buy at that price. And so I've sold to a QI, I sell with probability QI, and my revenue is QI times VI of QI, the price I post. Okay, and we can depict that on this plot. If I'm going to sell with probability QI, then I'm going to get they're going to pay me VI of QI, and my revenue is going to be RI of QI. This area here. And we can plot the revenue curve, which may, in some setting, look like this. Great. The marginal revenue is the derivative of the revenue curve. And I've taken the derivative using the product rule. Okay, and one thing to note here is that the virtual value of the agent is exactly equal to the derivative of the revenue curve. Okay, and one way to see this is to note that, well, QI is equal to 1 minus FI of VI. That's just the probability that the agent has a higher value than VI, and that's exactly what QI is, the quantile of the agent. And to note that that 1 over little fi, the density of qi, is equal to minus v prime I of qi. Okay, so plugging in those two identities, we see that indeed the marginal revenue is exactly equal to the virtual value via the usual formula. Okay, and of course we know that regularity is defined by monotonicity of virtual value, and thus we see as the virtual value is the derivative of the revenue curve. It's monotone if and only if the revenue curve is concave. And so concavity of the revenue curve and monotonicity of its derivative are equivalent to regularity. Okay, and of course, just want to conclude with the main theorem from Meyerson, Bulow, and Roberts, which is the expected payment made by an agent is equal to their expected virtual surplus. Okay, so here we see the expected payment of the agent is equal to their expected virtual surplus, which is the surplus we would get if we replaced their value with their virtual value, which is equivalent to the marginal revenue. All right, that concludes the first part of this lecture series.